Swayam Prabha. Digital India. Educated India.
Hello, so welcome to Astrochemistry. This is lecture 17, and in the previous lecture we had looked into the various molecules present in space and the scope they present for chemistry, the molecules that have been detected in space. Okay, and we started off with diatomics and gave some examples, diatomics, and gave the example of COCN, KCl, SiO, etc., and how they could, and also of SiO, which can form monomeric SiO4 4-, which could subsequently form SiO4 4- n times, that is polymerized. So we saw how like the various comets and asteroids, etc., can be formed starting from the diatomics. So the chemistry behind the comets and asteroids formation, we saw that is from the diatomics, and then we chose some examples of triatomic molecules, and we understood that we could, with the example of Mg, Nc, etc., the metal ions can actually aid in catalysis in space. We saw that they could do some catalysis in space. I didn't go through great details with the catalysis in particular, but we shall see more details subsequently. So we saw catalysis in space, and using the example of HCN and HNC, I illustrated to you the fact that in the ISM, thermodynamics is not the sole guiding factor, right? Thermodynamics, not the sole guiding factor. Okay, right? So thermodynamics is not the sole guiding factor. In addition, kinetics is also relevant. We discussed this in the differences between ISM and Earth also. I re-emphasize this point, and this shall be a point coming up again and again, so that it's very clear to you how much richness there is in the study of interstellar chemistry. Okay, so then we will continue with the recap. We studied about the tetraatomics, and I think the examples I gave you were of formaldehyde and ammonia. So ammonia is responsible for our understanding of the dense molecular clouds. That dense molecular clouds even exist is partly due to ammonia. And HCHO, I told you, could be responsible for further sugar chemistry, not happening in the ISM itself, but once HCHO polymerizes, it can give rise to a lot of sugars, which are very important and critical for our day-to-day functioning on Earth. Okay, so then the next example we chose was HCCN. This highlighted that carbon found in space need not always be tetravalent, right? For example, this is a reactive intermediate. It has a divalent carbon here, but still that could also be formed in space. So this is kind of where we stopped at lecture 16. Okay, and I told you that, if I recall, we shall be starting with a very interesting molecule in this class. Okay, what is the molecule? Say for example, I'll ask you this question. Okay, consider a molecule of the formula C3H. C3H. Now, what could be a possible structure? Based on your general chemistry and high school level chemistry, what could be a structure of this molecule C3H? What would you imagine? Well, what would be a starting point to answer such questions? You would say that, okay, so it is C3H. Now, it's carbon rich. I know that for alkanes, right, when I consider alkanes, they have the formula CnH2n plus 2. The number of hydrogen is going to be much larger than the number of carbon atoms present. The minute it is lower, I would think of multiple bonds present, correct? And the alkanes and alkynes. It is significantly lower. In fact, the ratio of carbon to hydrogen is 3:1. So therefore, I could only think of probably multiple double bonds, or a ring and a double bond, or a ring and a triple bond, something like that. I also noticed that this is it's a free radical system, because it's an odd electron species, right? Okay, so considering all this, what possible structures could you propose? What all possible structures could you propose? Also considering the fact that, we no longer have the restriction that carbon always has to be tetravalent. Yeah, you could propose some linear structures, correct? Yeah, you could propose some structures where, the 3 carbons are in a straight line and then the hydrogen is just attached with 1 carbon. That's of course there. What else? What else could you propose? Can you think of any cyclic structure? Okay, so if you think of a cyclic structure, what would be the facets involved? You have a carbon. I mean, the minimum number of atoms needed for a cyclic structure is 3. You have all the carbons. So let's just draw a cycle, C, C, C. And okay, so if this is the structure, right? Well, where should the hydrogen go? The hydrogen, let's say that I put the hydrogen anywhere. I just put it on top. Okay, so I have this entity. Now this is C3H. But the total number of electrons involved here are how many? So if you consider only the valence electrons, carbon has how many valence electrons? 4. So 4 3s are 12, plus 1, 13, correct? Now, I have to, distribute, and how many are here in the structure? 2 plus 2, 4, 4 plus 2, 6 plus 2, 8, right? And of course, I can call any center to be a free radical. For now, I start with this. So how will I fill the rest of the structures? I mean, well, one starting point would be to try to satisfy the tetravalency of carbon, in as many carbon atoms as possible, right? If you have this structure, the tetravalence is satisfied, okay, right? For other structures, say you want to put cumulative double bonds, you'd have carbon containing easily more than 4 valence, okay? So this seems to be the least unreasonable structure out there. And as it turns out, this is indeed the structure, the lowest energy structure of C3H. So lowest energy structure of C3H detected in the ISM. Now you may be wondering, okay, something is still amiss with the structure, right? What do you think is the problem? Based on what we know conventionally about chemical structures on Earth, what is one major problem? Well, if you have taken an introductory organic chemistry class, or even, when you discuss hybridization, bond angles and bond types in general chemistry, what's the problem here? You consider a prototypical alkyne. This is an alkyne, right? It's a cyclic alkyne. Now, when you consider alkynes, what would be the common structure encountered of alkynes? Well, what's the simplest structure? It is this person, right? What's this person named? I mean, this molecule. I'm sorry, I called it a person. What's this molecule named? It's called acetylene, right? Yeah. And whenever you see, like people writing the structure of acetylene, have you seen them write it like this or this? Why do you note that the structure is only this and not this or this? Well, it is because in the ground state, this bond angle has to be 180 degrees, right? Correct? Okay, this bond angle has to be 180 degrees. Are we all good? To define the bond angle, we need 3 atoms, right? Yeah. So it's a linear molecule. Okay. And so therefore, it's based on various concepts of hybridization, valence bond theory, all those things. Okay. We can discuss them in the tutorials if needed. Okay. So it's 180 degrees. But over here, what is the bond angle? Well, it has to be more or less a symmetric triangle. So it's close to 60, right? This bond angle here is close to 60 degrees. Oh my God, right? What's happening here? The molecule is going through so much stress. This is called as ring strain. Okay, more than stress is for human beings. Strain is the right phrase here. Okay, so this molecule is undergoing so much ring strain, whereas the normal bond angle is going to be 180 degrees. I'm talking about the CCH bond angle. That's 100 CCH, this bond angle, which is 180 degrees here. Now, in this highly strained molecule, it is 60 degrees. But even this is detected. Okay, but even this is detected. And of course, it also has one carbon atom, which is only trivalent because it's a free radical. Okay, so this is one possible structure of this molecule. But hey, this is not the only structure assigned. It turns out that this molecule has other isomers also. The other isomers, all of which have been detected in space. That is the key point. Okay. Now, let's call this structure 1, which is the lowest energy structure. So, there are going to be 3, there are going to be how many? 3 carbons and 1 hydrogen, right? Yeah. So, structures like this have also been detected. Right? Now, can you understand this, right? So, you have one of this structure, this is an isomer. And another isomer is also going to be this. Okay, so I'll call this 2 and I'll call this 3. Now, in the ISM, right, structures corresponding to 1 and 2 have been detected. The 3 I'm not so sure about. I'll check and inform you in the next class. Okay, so 1 and 2 have been detected. And in some cases, this is linear, but in some other cases, it is bent. Okay, so what does this example teach you? This teaches you the idea that, of course, unconventional structures can be detected in ISM, where you would expect a bond angle of 180 degrees with the molecules occurring on Earth. The bond angles can be highly distorted in space because once formed, right, it has nothing much to react with because the number density is so low. That's one reason, point number 1. And not just that, that's a point we've been seeing repeatedly in this course for multiple lectures. Okay, not just that. The first time this molecule, the fact that both 1 and 2, the structures have been detected in space. Okay, right? So the structures both 1 and 2 have been detected in space. And what does it tell you? It tells you that what are 1 and 2? They are actually isomers, right? What are isomers? Well, they have the same, at a broad category, there are different types of isomers, but broadly speaking, isomers have the same molecular formula but different chemical structures, correct? For example, one is cyclic and the other is acyclic and linear. Okay, now the chemistry of isomers is also possible in the ISM. This is the single important point from this structure. Okay, on top of the fact that unconventional structures can be found, which is a repetitive idea in this course, isomers are also possible in space. And this leads to a tremendous variety of unexpected chemistry. Okay, for example, if it is this structure that is going to be chemically participating in a reaction, the chemistry, that is the chemical reaction that is going to be happening is going to be different when this is the structure that is participating. And both have been characterized. Of course, you can ask me a very valid question. Well, how do you even see? First of all, I don't even know how molecules are detected in space in the first time. How do you even assign a structure to them, right? Well, if you haven't thought about this question, it's about time that you start thinking about these questions, okay? We shall very, very soon get into how molecules are detected in space and how are their structures identified, okay? Both are pertinent questions, but hold on for now. And please understand that both the structures have been identified, detected in space, and are identified to have these two structures. And the idea that this molecule teaches us, this triatomic molecule teaches us is that, again, a very simple formula, C3H, containing only 4 atoms, but it displays structural complexity. So it presents yet another example of a complex organic molecule in space, which teaches us about the idea of isomers and isomerism in space. Okay, so but we just saw, like molecules containing up to 4 atoms, right? Diatomics, triatomics, and tetratomics. Even with that, look at the variety of ideas for chemical evolution that we get in space. We talk about the concept of diatomics, and triatomics, giving us about giving an idea about how the various rocky versus icy substances may be formed, and then we got an inkling about the participation of metal ions in catalysis, and now we even have the idea of isomerism in space. So the space is replete with a tremendous variety of rich chemistry, even though the number of atoms in the molecule itself may be very small vis-a-vis what is found on Earth. Okay, so this is about tetraatomics. Now, of course, I can keep going on and on with so many more atoms and different types of atoms. But what I'll do henceforth is I will just limit myself, okay, to molecules with 5 atoms and more. Okay, so I mean, if I keep limiting myself to only the specific number of atoms present, then this discussion would go on and on and on, because the chemistry of each molecule is going to be essentially different. Nonetheless, we are trying to select key molecules detected in space, and from that obtain some kind of a representative idea as to what kind of diverse chemistry can happen in space. Okay, so now let's take the examples of molecules containing 5 atoms. The very first thing, and this is part of, I've been following a numbering system, if you notice, right? So for the diatomics, we started off with A, okay, right? And for the tetraatomics, it happened to be D, okay? And within D, this molecule is the 4th example. So this is D4. I am using this nomenclature, just so that there is a continuity in the molecules that in our understanding of the molecules detected in space. Okay. So for the molecules with 5 atoms or more, I begin with this nomenclature 5. Okay, the numbering system, I start with 5, E, and the first molecule we're going to be discussing here is, what's the simplest molecule containing 5 atoms? I've already given some part of the answer here. It's methane. Okay, now methane has been detected, and once we know methane has been detected, well, what about the chemistry of methane? You can form all the free radicals, you can form the carbocation, and you can form the carbanion. Now, of these 3 species, the carbanion, if I'm correct, has not been detected yet in the ISM, I'll confirm, but these 2 molecules, the methyl free radical and the methyl cation, have been detected. So I'll confirm if methyl anion has also been detected, okay, in the next lecture, but you can be assured that the methyl cation and methyl radical have already been detected. So all the alkane chemistry, that can happen in the interstellar medium. All right, this is one example. The next example is going to be, see, we saw that a molecule like HF can exist. Okay. We saw that a molecule like H3O plus can exist. Okay, right? Another example in the tetraatomics was H3O plus. We saw that, right, in the previous lecture. Okay, by that logic, this should be 5. Okay, so, and what is H3O plus? H3O plus is a proton donor, and it participates in acid-base reaction. Okay, is H3O plus an acid or base? It's a proton donor, so it's an acid, right? So, but what is the difference between HCO plus and HCOOH? Well, we talk about what's a strong acid and what's a weak acid, right? we have the discussion of the Lovey Bronsted theory of acids and bases. So HCOOH represents a weak organic acid. So we have a weak organic acid. And what are the ways through which it can participate in different types of chemistry? Well, one is the cleavage of this OH bond, which is its acid-base chemistry. And besides that, the C double bond O moiety. The C double bond O moiety is also where, you can form various intermediates and molecules by an attack of a nucleophile. So this is another example. The next example is going to be that of, this is an interesting molecule. It's C2H2O. Okay. Now, how do you write down this formula? C2H2O. What are the various possible formulas? Well, we'll begin with, like structures which have all 4 carbons valence satisfied, and then we can think of structures which are more complicated. So what could be this? Well, in the interest of time, I'll give the answer myself. It's going to be C double bond C double bond C double bond O. Now, this is an example. This molecule, C2H2O or ketene, is an example of what is called as a cumulenone. Cumulatively, you have ene and an one. That's it. Okay. So, what are the various modes of reactivity once again? Well, you have the lone pairs on oxygen. And then the double bond C double bond O and the C double bond C also. So, interesting molecules like this can be found. And then, of course, now that you have C2H2O, you can also have simpler alkenes. Simpler alkenes such as C2H4. Okay. So, which is nothing but this molecule, right? This has been detected. But interestingly though, whereas C2H4 has been detected, if I'm correct, C3H6, propylene, is yet to be detected. Isn't that again a fascinating idea? C2H4 has been detected. Its next analog, next higher homolog, C3H6, that has not been detected yet. Okay, so like this observation tells you how much more there is to understand about interstellar chemistry. Okay. So, and of course, what chemistry can CTH4 participate in? It's a double bond. It can undergo substitution, addition, etc., right? So, that is the various reactivity expected from an alkene. Okay. So, the next example is HCONH2. What is this molecule? It is formamide. Now, in the astrochemistry literature, it's also written as it's written like this, but a structurally closer representation would be this one. Okay, right? This is formamide. What is the importance of this molecule? Well, for the first time, we are encountering a CONH2 moiety. And where else do you find the CONH2 moiety? What does it resemble? You don't exactly find it, but in the proteins and amino acids, right? You kind of have a CONH2 moieties in some side chains, right? And you kind of see a resemblance going towards the amino acids, right? Amino acids are molecules of the formula, something like COOH, NH2, and some R. So in the side chains of some amino acids, you have the CONH2 moiety, but the idea that you have the CONH2 moiety gives you the confidence that it can be manipulated further to perhaps lead to the generation of an amino acid in space itself. So that is the relevance of this CONH2 moiety. Okay, so that is formamide, and of course it can react through various means. The NH2 is a good leaving group. It is a very weak base. Conventionally not even a base, but it can still act as one. The O can coordinate with so many other species. Okay, right? So by various associated reactivity patterns, this molecule can easily undergo so many reactions to further help in the chemical evolution of molecules in space. All right. So this is formaldehyde. What is the next example? So the next example we have is glycoaldehyde. See, we are now considering multiple functional groups. For example, the amide group contains the NH2 group and the C double bond O group. Okay. Now this molecule called as glycoaldehyde, that is, it has CHO and this is CH2OH. This is glycoaldehyde. Okay. Now what is its specialty? Again, with the fact that it has multiple functional groups, it can undergo different types of chemistry. Not just that. This is the dimer of formaldehyde. Now, in space itself, in the ISM itself, both formaldehyde and glycoaldehyde have been detected. So, well, have we looked into this before? Yeah, briefly while discussing, the tetraatomics in formaldehyde in the previous lecture. And not just that, even in the first one or two lectures, we discussed the fact that this molecule, we discussed about why it dimerizes. It dimerizes on Earth, but it doesn't do so in ISM. And what is the implication? The implication is that molecules' reactivity pattern is different in the ISM. That is what we discussed much earlier. Disregarding that, this molecule is also a critical connector to the chemistry of sugars and carbohydrates, because again, if you keep going further, you add one more CH2O moiety to this, you'll be getting HCHO thrice and 4 times, 5 times. By the time you go to 5 times, you encounter the common sugars encountered in our bodies. That is ribose, ribulose, all of those things. Okay, so this is again yet another critical interstellar molecule relevant in the area of prebiotic chemistry. By prebiotic chemistry, I mean the chemistry of the molecules responsible for the formation of life itself. Okay, so this is a molecule. Our next molecule is going to be a super interesting molecule. It is C3H6O. I won't make you guess much. I'll give you the structure myself. It is propylene oxide. Now, I'll write the name also. Propylene oxide. Now, so far in the last over the last 2 or 3 lectures, I have been giving you different structures. Okay, and we discussed various features. For example, unconventional structures, isomerism. I mean, ability to polymerize, ability to catalyze, etc. But looking at this structure, in this, each this is called as a bond line notation, where each edge represents a carbon atom. Okay, so it is understood that I'll write down the structure more. This is it. Sorry, carbon cannot, its valence cannot exceed 4, so that was a mistake. Yeah, this is it. So this is propylene oxide. Okay, this is just a shorthand representation of the same structure. Now, so far in this series of 4 lectures, have you ever encountered a structure similar to this? Well, in terms of being cyclic, yes. In terms of containing some functional group, yes. But this structure is particularly special. Can you guess why? Can you guess why? And what about this structure makes it so special? Any guesses? Anybody? What's happening here? Why is this structure very special? You might take a minute to think about it. The answer, as it turns out, lies in this particular carbon atom. That's a hint. What is it? Well, an even more obvious hint would be that this is a carbon atom of the form CABCD. So this is a chiral molecule. And in fact, it is the first ever chiral molecule detected in space. Why do we care about chiral molecules? Well, for that, and also some more interesting aspects about this molecule, we shall be encountering all of that in the next class. So please stay tuned for the next class. So to summarize, in this class, we looked at molecules containing 5 atoms and more, and what new chemistry they can lead us to. with respect to molecular evolution in the ISM. Okay, thank you so much.